Hi, everyone. Thanks for coming to my talk. I'm going to talk about efficient neural network verification using branch and bound. And I'm Suman Jana from Columbia University. This is joint work with several of my colleagues at Columbia and UCLA and CMU. So overall, we are going to talk about approaches to neural network verification that have been developed by my group in collaboration with the others. First, we're going to briefly talk about the motivation and the background, and then the challenges in neural network verification, and then how we address some of the challenges in our branch and bound based approaches. So in general, as we all know here, machine learning is increasingly being used in security and safety-sensitive tasks. And in these specific tasks, like self-driving cars or AI-based medical diagnosis, the correctness of the predictions are extremely important. And as we probably, again, all know, that despite their very significant progress, a lot of the state-of-the-art machine learning models are not quite accurate, especially at the presence of an attacker. There are several prior works showing different kind of mistakes these sort of networks make. For example, probably all of you have heard of adversarial examples where a state-of-the-art machine learning model, which predicts an input correctly in this context, the image of a cat, once the image has small perturbations specifically crafted to misdirect the model, will cause misprediction in the model. And this sort of attacks have been demonstrated widely in the recent past. And the key idea behind finding this sort of crafted noise is essentially to solve an optimization problem, as described here. I'm not going to go into the details of the problem. I believe most of you know about this. It's simply the idea of finding a smallest perturbation possible to the input that will cause the model to mispredict under some normed restrictions. And simple gradient-based methods for solving this optimization problem often work very well in practice. Therefore, finding such inputs are not hard. And neural network verification is one of the key ways of potentially guarantee correctness and thus avoid such mistakes potentially being made. So that's one of the key motivations. Of course, there are other kind of properties beyond just sort of adversarial inputs that one might want to check the neural network's input against. You might want to make sure that the neural network's input satisfies those properties. The actual properties often depend on the domain. All right. So having said that, let's take a bit of a closer look into the verification problem of the neural network. So what are we essentially talking about? At an abstract level, we are talking about a neural network which has already been trained, and then we provide a given set of input ranges in terms of the inputs to the neural network. And then the output must satisfy some sort of a property. In this very simple case, you can imagine that, let's say, the neural network's output had to be greater than 0 in this context. Obviously, this is not a realistic property, but this is just for an example. The problem with ensuring these properties with a strong correctness guarantee is that neural networks are by design highly nonlinear. As we all know, ReLU is a very popular activation function in the neural networks, and it has two linear pieces. As we increase the number of the ReLUs stacked into the neural network, the linear pieces, the number of linear pieces increase exponentially, and we'll end up with 2 raised to n linear pieces, where n is the number of ReLUs potential. So this obviously is a very hard problem. In fact, it has been shown that this is NP hard to track all the linear pieces and verify any sort of guarantees on the neural network in the worst case. Of course, ideally we want a verifier to be complete, What does that mean? That means it should always prove or disprove the property, given sufficient time. Of course, as I said, this is NP hard, so this is it's unlikely that we'll be able to achieve such a thing. So what's the next best thing? Often in practice, a sound over approximation might be sufficient. For example, if you can look here on the picture on the right, in order to satisfy the property f greater than 0, in order to say that the neural network satisfies this, you don't need to precisely bound the possible output of the network. Even loose bounds, as long as it can show that this property is satisfied, will be enough. Right? So this is what the picture shows. And this is what all the verifiers are essentially trying to achieve in practice. And in terms of verification, there is another kind of verifiers, as I said, this sort of verifiers which can give you this loose approximations. So these are called incomplete verifiers. And they are heavily used in the branch and bound based verification methods. I'm going to tell about what branch and bound based verification is in a second. So if you don't know about it, don't worry. And the other issue with incomplete verifiers is that they tend to have many potential false positives because their bounds tend to be loose. So in order to achieve soundness of the verification, that is usually guaranteed by the incomplete verifiers. Essentially, if some property can be verified, it ensures that there is no violation, but the other way around, the reverse statement is not true. That means if a property is said to be violated by an incomplete verifier, it doesn't necessarily mean that the property is truly violated. Okay? Okay, so having said that, let's take a look at the branch and bound based neural network verification. So the key idea is very simple. Essentially, there are two key steps. One is branching and the other is bounding. So given a safety property and given a robustness region over which we want the safety property to be satisfied, essentially branching will split the original problem into a bunch of easier subproblems. And bounding will use incomplete verifiers to try to verify each of these subproblems. And it will repeat this process recursively until the entire all the subproblems potentially have been verified. And this essentially is the key idea behind branch and bound. Now, before I dive a bit more in terms of the details of our group's work that we would like to talk about, let me give you a little bit more background in terms of branch and bound verifiers. So CROWN is one of the early branch and bound verifiers, which was published in 2018, on which we build on. The idea there is to build a generalized incomplete verifier using linear relaxations. As I told you, because the ReLUs have piecewise linearity and they're hard to keep track of, what CROWN tried to do is it tried to relax the ReLU into linear constraints. Obviously, in this process, you have to take some error. And the whole idea is to try to minimize that error. And what CROWN did is essentially it did two different types of relaxation, which is parameterized on this alpha parameter. As you can see here on the top, you have alpha equal to 1. So it has a different relaxation. And if you have alpha equal to 0 at the bottom, it has a different relaxation. So the trade-off essentially is that this will result in different kind of errors, right? Different kind of over approximation error, depending on which value you set, right? And they had a simple heuristic to decide which bounds to use when. Now, of course, note that this is just a heuristic. This doesn't necessarily give you the best behavior. And so just to see this in work, as you can see here, you have this very simple neural network, and you have this relaxation. In this context, the alpha value is set to 1, and then the final output you can get looks like this. And in terms of tightness, here are some of the past methods like naive interval or symbolic interval. Compared to that, CROWN, as you can see here, the output is -1, and the time taken to compute the output is shown here as well. So this is 0.1 second. Essentially, this is as fast as some of the prior methods, but the bound is much tighter, which is -1, where the ground truth is 0. Right, so that's the basic idea behind Crown, which was done by Zhang et al. And then we built our verifier, Alpha Crown, based on the relaxations of Crown. But our key idea is motivated by the question that in this relaxation, there is a parameter alpha, okay? And it is set either to 0 or 1 by the Crown folks. Then the obvious question is, does it always have to be that? Does it have to be 0 or 1? Or is it okay to set it in the middle? What is the effect of setting it? Do we always get the optimal error if we only set it to 0 or 1? And we found out that the answer to this question is that it doesn't. The optimal value can appear even when alpha is a value between 0 and 1. It depends on what the input to these RLUs are. And based on that, the optimal can appear in different places. Then obviously, the next natural question we asked is, okay, how do I find the best alpha, the optimal alpha for a given ReLU? Turns out that depends on what other ReLUs are connected to this ReLU, what output they are producing, and that is fed into our a particular ReLU, right? So then the question becomes essentially, can we optimize alpha to minimize this relaxation error? And obviously, as you can see here, the optimization of alpha has to be done jointly over all the ReLUs, because clearly there are cross dependencies across them. One ReLU's output is fed into another ReLU, right? So that's the basic idea. Essentially, what we do, we introduce an optimizable parameter alpha and relax each ReLU based on that optimization parameter. So essentially, every ReLU has a separate alpha based on which the relaxation happens for that particular ReLU. And then we jointly optimize all these alphas together with the actual verification process. So gradient ascent is what we use to optimize alphas. So essentially, this transforms the verification process into this joint optimization problem. As you can see here, we are trying to find the minimal value over x and y in this particular case for this simple property. And while we're doing that, we also want to maximize the output value based on the alpha. When we pick an alpha, that'll do this. So that's kind of the basic idea behind Alpha Crown that has been developed as part of our work together with several collaborators, as I mentioned. And as you can see here, the output is shown here. The Alpha Crown essentially achieves significant tightness over the original approach of Crown. As you can see here, in this particular context, the value is -1 and minus 0.75 for Alpha Crown. However, it takes slightly more time in this context compared to Crown, but it's still pretty fast. All right. So the basic idea of Alpha Crown at a very high level was also it was similar to the LP verifier that are used with triangle relaxation in the past. The main difference, obviously, with Alpha Crown is that we don't use the LP solver for this particular process. Our joint optimization is much faster than the LP solvers, the linear programming solvers. And this is kind of the main advantage. So if we use fixed intermediate bounds, in the sense we don't jointly optimize for alpha, we're still going to get similar tightness as the LP verifier. But if we do use the jointly optimized intermediate bounds, then we get tighter verification, the tighter bounds than LP verifiers. And this is not surprising because the relaxation, the triangle relaxation used in the LP verifier case was done in isolation, so that just relaxed individual ReLUs separately. So we have this dual advantage. First of all, our joint optimization can give us tighter bounds, as well as we don't use the heavyweight linear solvers in this particular way. So that has advantage, as you can see here at the bottom. The numbers are shown. Essentially, you have the LP verifiers that gives you, in this particular context, a value of minus 0.13, which takes 5 seconds. Alpha Crown is much faster. In 1 second, it can give you much tighter bound. In this context, is minus 0.04. Right. So, but what are the limitations of Alpha Crown? Well, first of all, it cannot handle the constraints that are generated by splitting a neuron. And remember, in the branch and bound, this is one of the main source of constraints. Essentially, in branch and bound, if you want to deal with the individual constraints for each ReLU separately, that's why you need to split the neurons. So this sort of constraints are not well handled by Alpha Crown. As you can see here, the LP solvers give you much tighter results for this sort of cases. But on the other hand, Alpha Crown is significantly faster on GPUs. So that has one of the main advantages over the LP solvers. And therefore, it can potentially enumerate very fast, especially with a GPU available. And the other limitation is that it cannot detect the infeasibility of a subproblem. And this is crucial for branch and bound performance, because you want to stop the exploring a subproblem as soon as you know it to be infeasible. And so this is another limitation. LP solvers can do this. So the implication of this is that the completeness of the verification process cannot be guaranteed by Alpha Crown alone. So in order to avoid this, in order to build a complete verifier, what we do for this Alpha Crown is we essentially use LP solver only for those hard cases. And this results in minimal LP solver usage, which can still give you fast performance for the common cases, which will be handled without LP solver, just by Alpha Crown. So that's kind of the basic idea. And once we build this complete verifier together with minimal usage of LP solver, we get around 20 times faster performance, as you can see here on the right-hand side. This is based on LP compared to the purely LP-based verifiers. And then now the next question we wanted to address is, how do we solve these two limitations, right? We wanted to be to avoid usage of LP solvers completely, if possible. So this was done as part of the next work that our group did. It's called Beta Crown. So the basic idea behind Beta Crown, remember, our goal is to solve two different problems, right? One is, how do we handle the splitted neuron constraints that LP solvers handled well, but we can't, right? So that's the first problem that we address as part of Beta Crown, and we don't want to use LP solver, right? So what we do is we create a dual problem through Lagrangian relaxation. So we essentially create an equivalent optimization problem, but in the dual space, right? So we have this, introduce these parameters beta, which are the relaxation parameters, and the beta has to be greater than 0, and we want to solve this optimization problem, right? So that's our key idea, and this is why we call it the Beta Crown. And the good property that we get from this dual relaxation is that any value of beta, as long as it's greater than 0, greater than or equal to 0, produces a sound lower bound, right? So if we optimize, if you can find better values of beta, obviously the bound gets tighter, but even if we do not find the optimal, we still get a sound bound. So that's a very nice property to have. And we want to obviously optimize X, Y, beta together. And if we find the best value, obviously, then it will be equivalent to what the LP solver will give us. And it also solves the other problem, which is detecting infeasibility. So if something is infeasible, the objective value of beta in this particular context will tend towards infinity. So it will become very large. So that kind of solves both of these problems. And because this dual problem is convex with respect to beta, we can use gradient descent to solve this problem. So that's kind of the basic observation behind beta crown. So as you saw that introducing this dual relaxation-based approach essentially solves the two main problems that Alpha Crown had, and we can thus avoid using the expensive LP solver for this problem. And as you can see here, this results in massive parallelization using GPUs that LP solvers cannot exploit. But because we are using gradient descent on this dual problems, we can now use the parallelization of GPUs. And as you can see here, in terms of the tightness summaries, it gives you very similar tightness in this context as the LP solver, but the performance gain is really large. In this context, it's compared to 10 second, when you're using branch bound and LP verifier, we get around 0.4 second, which is much faster, obviously. So that's kind of the main advantage of beta crown. And this allows us to perform fast verification of different types of neural networks. As you can see here, this essentially shows the running time for different models trained on CIFAR-10 dataset. And again, I won't go into the details of this, but essentially the performance gain is really large, around between 100 and 1,000x faster than traditional solver-based verifiers, and therefore, it pushes the state-of-the-art further. So we took this verifier, the alpha beta crown, and kind of competed in this contest called VNN Comp 2021, which is essentially a contest on a bunch of popular data sets of neural network verifiers. And alpha beta crown was the winner of this contest, showing the power of this approach. So in terms of conclusion, now that I have talked about these two different systems that we built, in terms of the conclusion and open challenges of verification of neural networks, we believe that the branch-bound approach to verification is very promising, but there is a lot of work that has to be done in terms of making this process more efficient and scalable, because despite a lot of progress, we still cannot verify really large models like the models trained on ImageNet or the language transformers. There have been some initial work going towards that direction, but we definitely need a lot more breakthroughs in order to verify them efficiently. Secondly, in this talk, we didn't explore that much about verifiable training. It has been observed, again, several of you probably know, that if you can train, as part of the training process of the neural network, if you use the verifier to guide the training process towards more robust neural networks, that tend to give you a higher verification rate, right? So the question is, how do we integrate the branch and bound verification process into this training process? So that's not clear, because branch and bound potentially can slow down, if used naively, can slow down the training process a lot. And then finally, how can we support richer properties? Because right now, the properties that we are verifying are essentially LP norm-based properties, which bound the perturbations up to some point. But in reality, you might be interested in supporting much richer properties. For example, in a self-driving car, a property you might want is, even if it rains, or even if the screen, the camera lens gets foggy, the car should still not crash. The question is, how do we encode such properties and how do we verify such properties? It's not clear at that point. Furthermore, you might want to make these properties to be aware of the cost of the cost to the attacker, if there is an active attacker in the setting. So these are some of the, I believe, very interesting directions that overall will be great to pursue. So with that, I'm at the end of my talk. If you have any questions, please do ask. Thank you. Thank you again.